Okay, time to get started. So here's where we were last time. We were looking at this example. One of several methods that I've shown y'all, in the process of showing y'all on how to create parameterizations. By the way, it's super important to be able to create parameterizations, because parameterizations are going to be how we get a foot in the door for computing this thing that we're about to define called a surface integral. It's going to be a big deal. It's going to be one of the major players in our discussions in Chapter 7. Okay. All right. So anyway, here we go. So the big idea of this one is that if you have an existing parameterization, for example, this, aka that, is a parameterization that we found by convenient methods. We know how to use the spherical graph parameterization in particular. And so we know how to parameterize the unit sphere, aka something with that equation. Now, I claim that there is a similar surface that we can parameterize kind of based on this as a starting point. So in particular, we're going to look at this ellipsoid. Now, is this a similar surface? How similar? Well, look at these two equations. I mean, they're not the same, of course, but structurally, I mean, there's a lot of similarity there, right? In fact, I can see exactly how to turn one equation into the other. For example, all I have to do is everywhere I see an x, replace that with x over a, and likewise for y and for z, right? So there's a simple little algebraic tweak that we can apply that literally turns the green surface into the blue surface. So they're pretty similar in that sense. Okay. All right, so with that observed, just, that kind of sort of plug-in sort of a thing, how does that affect the parameterizations? And there's a couple different ways to think about this. One way to think about it is to look at these equations. And where did I from that get these equations that parameterize my new ellipsoid? Well, it says right here in purple that all I have to do is replace every x that I see with x over a. So I did. Right? It's right there, right? That's all there is to it. Okay. All right. So that's a neat point of view. Likewise for y's and z's, of course. So, pretty cool point of view. Now, technically, if you want to get real uptight about it, technically this is not yet quite a parameterization. To be a parameterization, I need to have explicit formulas for x, y, and z. Okay, sure, fine. Solve for x, y, and z. Super easy to do. Okay. All right, now, here's a different point of view on this. Kind of more of a geometric kind of take, which I think is useful. By the way, of course, algebraic methods are reliable, right? They plug and chug, and that's a good thing. I'm all for algebraic methods. But geometric intuition is fabulous also in different ways for different reasons, right? What I love about geometric intuition is it helps you get satisfaction. It helps you keep track of what you're doing, having some sense for why you're doing what you're doing. So that this isn't just, apparently you just take this and you stick that in there and poof, it works, but you don't really know what's going on. So anyway, a geometric take is that I understand this little move that I had to do to turn the first equation into the second equation. I understand that geometrically. Right? We talked about this back in Chapter 2. If you have an equation and everywhere you see x, you replace with x over a, what you're doing is you're taking that original surface and you're stretching it by a factor of a in the x direction. Right? So that's, again, goes way back to Chapter 2. Okay, so thinking about it geometrically, apparently all of my x coordinates need to increase by a factor of a. All right, well, that's what your x coordinate was. Right? And increasing it by a factor of a. Cool. Done. Right, so yeah, it's a different point of view on the same thing. I mean, here I had an equation that x must satisfy. Here I had a explicit formula for what the values of x are. And in either case, we're just taking the values of x that used to work and ensuring that they have to be a times as big to continue to work. Okay. Now some students get unhappy about the fact that, do I divide? Do I multiply? Right? It kind of looks like I multiplied there, but I divided there. Are these even really the same answer? Well, yeah, of course they are, because don't forget what a parameterization is. When I say I have R, what that means is that that's X, Y, and Z. And don't forget, furthermore, you have to solve for that X and likewise the Y and the Z, if you want to call that a parameterization. So that said, this formula for X, is that the same as what I would get when I solve for X there? Yep, totally the same. Right? Solve for X on the right, that A in the denominator goes into the numerator. It's the exact same equation. Okay, how are we doing? Everybody happy? Okay, nice method, and comes up surprisingly often, by the way, that you find yourself with something, and by the way, ellipsoids also not particularly rare. That comes up, right? And if you want to parameterize that, start with something you already know. You already have a parameterization, right? And then just think about how to tweak it. Okay. All right, now that's all I'm going to show you for parameterizations. There are more examples in the book, but the thing about the book's examples, they're mostly about interpreting given parameterizations. And that's cool too, right? It's nice to be able to look at a parameterization and say, hey, what is this thing? Right? But yeah, my personal experience has been that it's just not what comes up, right? And so y'all are mostly engineers, all exceptions granted, of course, but in your engineering experiences, I have to imagine it's not that different from my physics experience, and I was given some problem where there was a circumstance where there was a surface, and guess what? It didn't come to me pre-parameterized. It came to me described in some other way, and I had to create the parameterization to work with, right? So examples where the parameterization is just given, I find a little bit unrealistic. And I think you'll find that what I've given you here, these, how to make parameterizations, I think it's going to be more useful in the long run. Okay. Okie dokie. Now this whole page, you'll notice it says for students to read. I think it's a pretty straight read. It's a nice point of view. You create something called coordinate curves. Ultimately, no big deal. Let me just hit the real quick highlights. And the big idea is here we have a parametric surface. We have position as a function of two variables. If you were to fix a value of t, t no longer allowed to change, t now a constant. Well, check it out. You have position as a function of one variable. Position as a function of one variable, what do we call that? We call that a parametric curve. Right, so it's not that deep of an idea, but if you have a parametric surface, fixing a variable creates a corresponding parametric curve that sits inside of your original parametric surface. And so here's an example. Take a look. It's, again, pretty straight read. Cute little observation here about the partial derivatives of the surface parameterization being velocities of the coordinate curves. And that's just something you just have to write it down, and yep, sure enough, wow, look at that. They're exactly the same thing. Good little exercise. Think it through. The punchline that we're building up to is as follows. Given this parameter, whoops, I wanted to be in highlighter mode. Given this parameterization, if I were to look at a little piece of area in the parameter space, you could probably guess where this is going, right? If I have a little piece of input area, and if I want to understand the corresponding little piece of output area, what I need to be able to do that, I need to understand, wrong, I want to be in pencil mode, sorry. I need to understand these input vectors and what are their corresponding output vectors. Now, again, different points of view you can take on this. You can use this idea of velocities of coordinate curves. It totally makes sense. And again, think it through. Here's a different way you can do this, though. Something that doesn't require coordinate curves at all, frankly, is, well, look, forget about the areas. We're just talking about vectors. And I have input changes, and I want to know the corresponding output changes. We already have a tool for that. It's the derivative matrix. And you can, no problem, totally fine, just write down the derivative matrix of this parameterization. There's only 6 elements in that matrix. You just write them down, right? And then write down what these vectors are, right? So d phi E1, d theta E2, and then literally multiply the derivative matrix by the inputs. That gives you the outputs, and you'll get exactly these formulas right here for those little edge vectors. So I think that's another nice exercise. I want to encourage everybody. I just told you exactly what to do. Just write it down and do it, and there it goes. Okay. All right. So all of that said, here's why we care about that. Now that we have output areas written in terms of, well, not really written in terms of input area, but I can get my hands on this output area. I know how to compute, in particular, the area of a parallelogram. Area of a parallelogram is the magnitude of the cross product of the edge vectors. And I know these edge vectors just computed on the previous page. All right, that's just chapter 1 formula applied to those known formulas for those edge vectors. Oh, and then furthermore, I also can say these scalars, like this scalar right there, d phi, it's a scalar. It's a scalar participant in a cross product, factors out of the cross product. Leaving it as a scalar factor in a magnitude, factors right out of that magnitude, and altogether it just factors right out. And likewise, this d theta factors right out. And having done that, now we really do have a formula that relates input area to output area, and our stretching factor, the factor by which green gets magnified to become blue, is that right there. Handy formula to make sure that you know. We're going to be using this a lot. Comes up tremendously. The magnitude of the cross product of the partials. As it turns out, and again, there's why, right? But this stretching factor is going to come up tons. And so do make absolutely sure that you have that memorized. And I think it's a great idea to have a good intuitive sense for where it comes from. Like so. Okay, how we doing? Let me hit the pause button real quick. Anybody have any questions? Everybody all right? Okay. All right, so here's the thing. It turns out that this vector itself, not the magnitude, just the vector itself, also interesting. And the reason why, before I get to the punchline, this vector, it's a magnitude, is a cross product of a couple of partials. We know from back here that the partials point in the same direction as those position differentials. Those position differentials are tangent vectors. So that means the partials are tangent vectors, and if your partial derivatives are tangent vectors to the surface, then I hope it's no surprise if I claim that their cross product is perpendicular to the surface. Right? So that makes this thing what we call a normal vector. You all have heard that term before. It's a normal vector. This thing is a normal vector. And it ends up being an important one. We all, in some sense, already know why. I mean, its direction is geometrically significant. It's perpendicular to the parametrized surface. Its magnitude is algebraically significant. It's the stretching factor that, of course, we're going to use when we eventually do a pullback. We're going to be doing pullbacks with this. And so a pretty handy-dandy thing, and it's nice to have a name and a notation for this. So the typical notation for this is to use the letter capital N. I've seen this in many multivariable calculus textbooks, so, fine, no problem, makes sense. The terminology is, terminology is always a little different in every book. Our book calls this the standard normal vector. Okay, well, first of all, let me explain why that makes sense, why that's reasonable. This formula is a standard formula that gives a very useful result for any parameterization. That's cool, right? So I get it, right? Standard makes sense in that sense. Here's why I don't like it. It's standard to the parameterization, not to the surface. The surface has lots of parameterizations. There's many different ways to parameterize, right? One of our big takeaways from chapter 1 is, there's a bazillion different parameterizations. They're not unique in any sense. There's no canonical standard parameterization, right? So when you call something that's peculiar to a single parameterization a standard, to my ears, I hear a point of view that makes it sound like you're saying it's standard to the surface. And of course, now I understand that that's not what they mean, but you can see how it could be misunderstood in that sense. So to me, this terminology, standard, is a little unfortunate. It's just terminology. It's not right or wrong, but I don't care for it. My idea is that this is specific to the parameterization, so I like to call it the parameterized normal vector. I just think that is more naturally pairs it with the parameterization that it must be paired with. Okay. All right, just terminology. Notice that means that we can rewrite our formula for the stretching factor like so. Right? And this is kind of an easier way to remember that stretching factor. It's just the magnitude of capital N. And then just remember the formula for capital N, which you were going to have to do anyway. So that makes that convenient. Okay. All righty. Pausing again. Everybody okay? All right. Okay. So let's do one. We know how to do area stretching factors. And golly, where did stretching factors come from? And the very first time we heard that term was when we did change of variables, in which case we were doing pullbacks, right? So we are ready to do pullbacks. We've got this parameterization, you might say pushing forward, and now we're going to take integrals and pull back. We're going to take, for example, maybe I want to compute the area of this first octant portion of the unit sphere. How would I compute that area? Well, I'd be adding up a bunch of those little DS's, right? How would I pull that back? Well, that would be represented by some sort of a rectangle over here, right? And I can figure out what that is by doing the corresponding integral pulled back to the green region, right? Just like every other pullback we've ever done, whenever you have a function that pushes forward, you can pull expressions back. Okay, now what we're going to do, the example we're going to do specifically asks what is the area of the entire unit sphere, the whole thing. Right, the entire sphere. How are we going to find the area of the entire sphere? And so then we're going to be looking at the corresponding full range of possible values of phi and theta. And again, it's just a pullback. Okay, so here's how that works. We know we're going to have to compute the stretching factor. Let's get that out of the way. There's a lot of tedium to it, and you'll notice that I yada significant amount of that computation, and this is something I want you all to do. I think this is a good exercise. Everybody should do that once in their lives. It's not that bad. It'll take you 5 minutes. It uses the Pythagorean identity 3 times, as I recall. But it's just kind of surprising that it works out this way. I mean, this complicated vector has a very simple magnitude. That's kind of cool. Anyway, check it out. Give it a try. Notice that we are following the process described here, which is first we have to find a parameterization. Then we have to take the appropriate partials. Then we have to take the cross product. And then we have to take the magnitude. 4-step process, you might call it. And that's exactly what I've done here. I've got a parameterization. And then I took the partials. Right? And then I took the cross product. Check me on the algebra. Make sure I didn't mess that up. More to the point, make sure you can do all of that. Right? And make sure you can do it proficiently. Keep in mind, math is not a spectator sport, right? You got to be able to get in there and actually do it yourself, right? So make sure that you are reliably, proficiently capable of doing all that. Quick pace, no mistakes, right? Make sure you're good with all that stuff. And then, having found the capital N vector, we take the magnitude to get our stretching factor. So again, a bunch of tedium. Make sure you can do it. Okay. And with that done, it's all over but the shouting. We want to add up a bunch of little pieces of area. Okay, how do we add up little pieces of area? Well, output areas are stretching factor times input areas, just like we discussed before, just like every other pullback we've ever done. Right? So this is the where the pullback happens. This is where we take an integral on the output space and pull back. This is now an integral in the input space. Okay. And we know what the stretching factor is. Stretching factor is sine phi, and that leaves us with a pretty doable integral right there, and the answer is 4 pi, which we all learned in high school geometry class, and this is a computation that confirms that old formula from high school geometry. How we doing? Everybody all right? Okay. All right. So a quick little sort of taking stock. Let's summarize what we have here. There's been a bunch of players that have been involved in everything we've done. We talked about parametrizing surfaces. I've waved my hands at the idea of finding these edge vectors. Those edge vectors, and of course you can think of them as coming from these partial derivatives, whose cross product gives you the capital N parametrized normal vector, which tells me how to relate input area to output area, etc. So this is just a bunch of stuff we've already talked about. It's kind of nice to have it all in one place. Here's some calculations that we've already done. We've already realized that that's that. A quick little observation, that vector, it's a vector, so it's got a magnitude and a direction represented by the unit vector. And when you write it as magnitude times direction, well, the direction is that unit vector, the magnitude is, well, the magnitude. So just another way to write it. That's going to be handy coming up, possibly today. Depends on how fast we go. So all that's old news. The only thing new here is the observation that when it comes time to take your parameterization and start doing partials of it, just don't forget your parameterization is just literally telling you X, Y, and Z. And so taking a partial with respect to S, you're just taking the partials of the coordinates with respect to S, and you can just straight up write that down like I just did. You're writing it, the whole thing, in terms of coordinates. Fine. Likewise on the other side. And then, by the way, you can take this cross product and you can crank that out by coordinates. no tricky curves. Y'all know how to do cross products. Just multiply it out. And it turns out, and at a glance, this is a real surprise. Weirdly, the coordinates of your capital N vector that come from a parameterization of a two-dimensional surface in 3 space, those coordinates are two-dimensional change of variable stretching factors. Isn't that weird? It's pretty surprising. The first time I saw this, I thought, oh, come on, there's no way. That's come on. How could that be? It's very surprising. It's also a really cool little story, and I mean, it's a math story, right? But there's a really good reason, ultimately, as to why this turned out. It's not a coincidence. There's a very natural reason why. And we don't have time to talk about it. And there's so many instances of that in this course. So much material that we have to do, and therefore so much that we have to, tough decisions and all that. So you're not responsible for knowing why these are two-dimensional change of variables stretching factors. But if you're curious, I'll be very happy to show anybody who wants to hang out after class, office hours. If you're curious, happy to show you. Okay. All right. Okay. Here's a nice special case. This is not, I emphasize, an alternative. This is a special case that's good for streamlining purposes to also be aware of, but I cannot emphasize enough, if you want to be able to do these kinds of pullbacks, you have to understand how to parameterize a surface and use this formula for the capital N vector. There is no substitute. Okay, that said, in the special case, comes up fairly often, in the special case where your parameterization is a graph parameterization. So you look here at this equation here, that's a graph, and so there is the corresponding graph parameterization. In that special case, there's a lot of patterns that just kind of always work out exactly the same way. So you'll notice, for example, anytime you do a graph parameterization, you're going to have S and T, or whatever your parameters are, right there in the first position. The partials are always going to be like that in the first 2 coordinates every time. Right? And that means that when you do the cross product, you're always going to end up with a 1 right there every time. And these other coordinates will end up being, as I have written here, every time. It's just a graph parameterization is a highly structured thing, and we can just carry forward like I've done here. And so the nice punchline, when you take the magnitude of that capital N, it'll always be this. So you could totally just memorize that formula, right? And then I cannot emphasize this enough, when you have a graph, and when you furthermore are using a graph parameterization, then this has all the computation kind of done for you, right? You don't have to write down the parameterization, take the partials, take the cross product, take the magnitude, right? All that tedium, we've already done it. Boom, here it is. Here's what the answer is going to be. Just plug right in to this formula. Very cool. I encourage you to have that memorized for use in just such an occasion. But again, I emphasize that's a special case. It will not work for every surface because not every surface can be parameterized with the graph parameterization. So you got to make sure to know this business as well. Okay, related note. Just an observation here, but if you look at this stuff there, that is magnitude squared of the gradient. Right down. That's what it is. Oh, and don't forget furthermore that the magnitude of the gradient tells you how steep the graph is, namely how steep your surface is, the surface that we're talking about in the first place. So here's another nice point of view on this. I think it is also really cool to know square root of 1 plus the square of the steepness. Pretty handy little formula to have understood. And then, so if you know how steep the surface is, then that, again, boom, instantly tells you your area stretching factor. And I'm going to show you an example where I think this is really cool. By the way, this might save you some money someday. I don't know how much y'all know about home maintenance. Right? It's a shocker, though, when you buy a home and, there's something wrong with you need to replace the roof on the house, and then you look at the price quote, how much it costs to put a roof on a house. Oh my gosh, I've spent less on cars. It's a lot. It's 5 digits, right? It's a tremendous amount of money. It really sticker shock. So now, where do they get that price quote from? Well, of course, it depends on materials and labor, blah, blah, blah. Well, how much materials do they have? Depends on the area of your roof. How much labor? It depends on the area of your roof. Right? So this 5-digit cost is going to come down to computing the area of your roof. And if you think about it, your roof is made up of some pretty weird shapes. I mean, there's a triangle there, but it's not a right triangle, and it's kind of tilted upward at some angle, and I mean, at a quick glance, it kind of feels like you're going to have to get up on the roof, and you're going to have to, measure that distance, and then, this distance, and then do a little geometry. And then you're also going to have to figure out the area of this parallelogram, which means, among other things, you're going to have to know that angle, because it's not a right angle. Right? So, I don't know if you've ever been on the roof of a house before, but it is really scary, and there's concrete down below. It's not like pillows down there, right? It's scary. I don't do it. I'm scared. I'm not going to do it. If I fell, oh my God, right? So how am I going to figure out the area of the roof to make sure that they're not, accidentally mismeasuring the area to the tune of maybe they overestimate the area by 15%, right? Let's just say, right? That could end up costing me a couple $1,000s. And can I just eyeball estimate that they're off? No, I would never know. If you don't compute the area, you will never know, right? And again, couple of grand, poof, gone. So here's the solution, and that is to make the recognition that the roof is a graph, right? Above any point on the footprint, there's exactly 1 point on the roof. It's a graph. So we can apply these ideas. And the punchline is that our stretching factor just depends on knowing how steep the roof is. And the really cool fact is that in many cases, all exceptions granted, the following statement I'm about to make is a statement about architecture. It's not a statement about like math or anything. But it just tends to be in a lot of houses, mine included, every point on the roof has exactly the same steepness. Again, all exceptions granted. Well, if that's the case, if the steepness is a constant, then that means that the stretching factor is a constant, and constants, the stretching factor now being a constant, factors right outside of the integral, and all we're left over with then is the integral of dx dy, in other words, the footprint area. And the footprint area is very easy to measure. It's all rectangles. And it's rectangles that I can get to on the ground, safe and sound, right? And that I am totally willing to do. Okay. All right, so I think this is a pretty good method, so you can double check and make sure you're not inadvertently being overcharged by thousands of dollars. I strongly advise, personal matter, right? This has got nothing to do with math, right? But I will never not do this if I'm the one paying, right? I'm just going to have to check that. By the way, for whatever it's worth, little side note, again, non-math, I can't help it, but I'm a numbers guy, and I have checked the math on quite a few significant expenses that I've had in my life, and I have caught errors several times. It's been many years, right? But I have caught errors, air quotes, errors several times. And wouldn't you know it? What are the odds? They're never in my favor. Weird, right? So anyway, for whatever that's worth, buyer beware, and I encourage you to double check stuff like this. Okay, moving along. So by the way, we're done with section 7.1 now. Moving on to 7.2. Where we were going with all this parameterizing stuff is how to define surface integrals, and we're going to do a bunch of stuff with surface integrals. It's kind of a ripoff, by the way, of the old idea of line integrals. And here's just, looking back in the notes to wherever that is, section 6.1 anyway. Here's how we develop the idea of line integrals. We're going to do really, really similar things over here talking about surface integrals. Really similar, right? I in fact tried to lay things out on the page to emphasize this similarity. So in particular, I can make little observations like, well, look, if you have a curve, and if you've got something that accumulates over that curve, well, then we can look at, sort of one piece at a time, and on each little piece, we can talk about stuff per unit length times length. All right. Well, we're going to do something really similar for surfaces if I have a surface. And if there is some quantity distributed over that surface, some accumulating quantity where the whole is the sum of the parts, then yeah, I'm going to look at one little piece of area at a time. And on that little piece of area, I'm going to argue that stuff is stuff per unit area times area. It's a shameless ripoff of exactly the idea that we did to define line integrals. It's just now it's area instead of length. It's a surface instead of a curve. Same basic strategy. Is that cool? Everybody see how it's, kind of stealing that old idea? Okay. All right. Okay, we're going to steal the notation as well. Deltas we write with D's. Limit of a summation, we use integral symbols. The domain, the surface itself, over which I'm adding stuff up, we make a subscript. It's just exactly what we've done previously. The terminology is a pretty shameless ripoff. We're going to call this a surface integral, because it's done over a surface, right? And then there's this mysterious, not clear why we need to clarify, but I am going to call this a scalar surface integral. By the way, the book uses this same term, which I appreciate. Scalar surface integral because the differential is a scalar, the integrand is a scalar. And again, as you're saying, well, of course they are. Let me just remind you, we've already seen an integral in which really most naturally written the differential is a vector. And the vector and the integrand is a vector, right? So vector line integrals. We have vector field integrands, we have vector differentials, right? And it came up perfectly naturally. So, in the same way, as it turns out, and this is a little foreshadowing, right? I've got a lot of stuff that has to get fleshed out first. But in the same way that, we had scalar line integrals and then this different thing called a vector line integral, we likewise, in addition to this scalar surface integral, we are soon going to fairly naturally stub our toes on something that we're going to have to call a vector surface integral. And it's pretty wild how it comes up. I think it's super cool, but that's, again, just a little foreshadowing. So for the moment, this is the sort of the foot in the door version. This is the scalar surface integral. Okay, how do we compute? Well, let's go back to line integrals. How did we compute an integral over a curve? Well, we parameterized it. We made it an image. This is one of our big sort of strategies. If you don't like a domain, make it an image. Right? This worked for change of variables. It's worked for line integrals. And now it's going to work for surface integrals. So big idea, we don't like our domain. I don't like this for sort of dimensional reasons, right? It's dimensionally awkward. It's a one-dimensional thing in a two-dimensional world. That's weird. Same thing here. I don't like this domain, this surface, right? I don't like it. And again, kind of for dimensional reasons. It's a two-dimensional thing intrinsically. There's no volume of a surface. It's an area. Right? It's a two-dimensional thing, but it lives in a three-dimensional world. And again, that's weird. I don't know how to get our hands on that. So in the same way that we parameterized the curve and then did a pullback, we are likewise going to parameterize the surface and do a pullback. Okay. All right, and good news. We've actually already kind of done all the work on this. We've already talked about the stretching factor, right? The area stretching factor here is magnitude of capital N, where capital N is this formula right there. And so, if once you know the stretching factor, pullbacks are just a matter of plugging in. I mean, it's you very much so. You just plug in the formulas. And so our stretching factor here, right, we plug in these blue areas that I was adding up are just now stretching factor times these green areas that I'm pulling back to. All your x, y's, and z's are functions of your parameters, s and t. Plug in, pull back, and what you are left with is an integral, all of which is in terms of s and t, and we have successfully pulled back this surface integral, this scalar surface integral. We've pulled it back into the st plane. Let's do one. Let's see this in action. I always get ahead of myself on this. I get excited about an example coming up. We do need to talk about this concern. There's the concern that this thing that clearly doesn't depend on the parameterization. I mean, look, that comes from a surface. Surfaces have lots of parameterizations. None of them are truly attached to a surface. We're going to compute it by way of a formula that seems to depend on the parameterization. By the way, don't forget, N also depends on the parameterization. A lot of the right-hand side here depends on the parameterization, or so it seems. How do I know I won't get different answers with different parameterizations? Well, this can be addressed, and neat fact, doesn't matter. Not obvious. Not obvious at all, but it is true. And by the way, the proof's in the book if you want to see it. It's not really course appropriate, in my opinion, but if you're curious. Okay, so lucky break. Don't have to worry about that little nasty point. Here we go. Let's do a computation. By the way, again, with the analogies, don't forget our first examples. Our first examples of scalar line integrals, I talked about one curve, and then I asked various different questions about it. What's the mass? What's the coordinates of the center of mass? What's the moment of inertia? Blah, 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 right? Various different questions. Same thing here. I'm going to describe one surface and point out there's a lot of questions I can ask about that one surface, namely how much mass is on it, what's the location, what are the coordinates of the centroid, and again, what's the moment of inertia. What these computations are aren't really the point, right? So basically the same physical concepts that we're going to compute here, but same basic idea, that there's a computation that I have to do first to get the stretching factor, And then everything else is plug and chug. And we're going to find the same thing here. There is a computation to figure out the stretching factor. And once you have that, everything else is plug and chug. It's just like with scalar line integrals. So let's see here. Let me zoom in. Here's a computation that I'm going to say everyone should do. In fact, this is a computation that I've already suggested everyone should do. You may even recognize that for the unit, for the unit sphere, that's a parameterization. And we've already, I've waved my hands anyway in the general direction of the computation that shows that the resulting stretching factor is sine phi. So again, I think it's a cool calculation. I think everyone should do this once in their lives, and it's your turn, so give it a try. If you get stuck, if you have problems, come ask me. Happy to help, of course. Okay. So with that done, off we go. We've got our stretching factor. Mass, the accumulation, follows the sum of the parts. Mass is mass per unit area times area. Right? No problem there, I hope. Output area is stretching factor times input area. That was our big conclusion from earlier, from a lot we've done today. And let's see here, the stretching factor, we just got through computing. The stretching factor was sine phi, as we saw up here. I'm largely just plugging in. Now there's a couple other little details. Let's see here. Where did I get Z from? First of all, how do I know the formula for density? Given. Right? So sometimes it's right there looking at you. How did I evaluate Z? How did I know what to do with Z? Well, don't forget your parameterization is literally telling you X, Y, Z. That's what it means to have a rectangular parameterization, is you're giving rectangular position as a function of parameters. Right? So I have an explicit formula for Z already chosen. It is part of my parameterization, and so Z is just cosine phi. Is everybody happy? Okay, all righty. One other little detail. Where'd these bounds come from? Right, y is theta from 0 to 2 pi and phi from 0 to pi over 2, and that is because of what the surface actually is, right? And it says right here, upper unit hemisphere. So we've got our here's a sphere. A sphere goes kind of all the way around like this, right? So just looking just at the top half, theta goes all the way around 0 to 2 pi, and on that top half only, phi starts at 0 and goes down to the equator where it's pi over 2. Everybody all right with that? And so when I do the pullback, these then are the resulting values of phi and theta. Okay. All right. Likewise, for the other calculations, so many similarities. Now, of course, we have a different starting formula. Mass is computed by that integral. The x-coordinate of the centroid is computed, of course, by a different formula. It's a different thing. So, of course, a different starting formula. By the way, notice that we need the result of the mass calculation to be able to plug into there. So that's annoying. But anyway, thankfully, we've already computed that mass. There it is. But again, it's just a matter of a lot of the same kind of plug and chugs. Mass is mass per unit area times area. Output area is stretching factor times input area. By the way, other things like X. How do I know what X is? Well, X, boom. First output coordinate of the parameterization. That's what X is. Right, so a lot of that stuff is the same. Oh, don't forget our stretching factor is, of course, still the same. Yada, yada, yada. Everybody okay with that one? Okay. Okay, and again, just like I did with line integrals, here's a couple more examples. I encourage you to give those a look. Make sure you are good with all those details. It's just details, and it's, again, mostly highly analogous to what we've already done. Okay, moving along. All right. Let's see here. Let me do that. Flashback, chapter 3. Oddly, seemingly out of place, flashback to chapter 3, but we've talked about this thing called flux. Right? We derived this formula right here. And remember what the point of that was. The idea of flux is that we've got some fluid that's flowing along, and as that fluid flows along, it will pass through whatever surface we have here. And if I know the flow, if in other words, if I know, either the velocity, wrong color, the velocity of the fluid flow, or maybe density times velocity, depending on my interest, depending on what I'm, depending on the circumstance, right? Then I can ask the different question: what's the volume per unit time, or mass per unit time, depending again on what I'm interested in. What's the total amount in whatever sense of fluid per unit time passing through that surface, right? So we start with this idea of a velocity. That's distance per unit time. That's talking about one little piece of fluid. Flux is talking about total quantity, like volume or mass per unit time. It's not talking about just one piece of fluid. It's talking about all the fluid, and furthermore, how does it relate to the given surface? Right? So flux is a more sophisticated concept. And again, boom, easy, handy-dandy formula that we've already computed. Does everybody remember this idea of flux? I hope. If you're maybe a little shaky, maybe it's a distant memory, foggy memory, this would be a good time to go back and refresh that. Maybe re-listen to some lectures, or I guess more accurately, because of my technical difficulties, go back to a past semester and listen to analogous lectures. All right. Okay, so we're going to take this, run with the ball, recognizing that this does assume that your vector field is constant. Right, that was important to the calculation. That's part of how I could argue that this was actually a parallelepiped. And the calculation we did involved that being a parallelepiped. It also assumes that our surface is flat. Again, parallelepiped. That's got to be that. Okay. So here's a recognition of how we're going to transition to this into a real world scenario. Sometimes your vector field is not constant. In fact, usually your vector field is not constant. And sometimes your surface is curved, not flat. And again, usually, right? Most of the time. You got your rare circumstances of like a table or something where the surface is flat. The world is full of bumpy, wiggly, non-flat things. Right? Okay. All right. Quick flashback. Going back to the chapter 6 take. We considered an old physics concept, namely work, but an old physics concept for which we had computed a result that comes from dot products, right? That relies on the vector field being constant and the domain in question being flat. And that's exactly what we have here, an old physics concept that we argued that we can compute with a dot product the calculation of which assumes that your vector field is constant and your thing is flat. It's very, very similar scenario. So how are we going to get our hands on this? Well, again, we're going to steal the good idea. The good idea for that led us to vector line integrals is we say, okay, well, yeah, curvy, non-constant, all sorts of problems. Break it up into little pieces. On each little piece, it's simple. And then we add up over all the pieces. We're going to do the same thing here. Big picture, that is, we are going to take a non-constant vector field, right, going through a non-flat surface, which I don't know how to deal with. And we're going to say, all right, well, look, sure, that's a hard question. Yikes. But if I were to look at one little piece of surface at a time, that little piece of surface is approximately flat. It's pretty close. It's not perfect. We'll deal with round-off errors with a limit, but that's pretty decent estimate. And then likewise, the vector field, it might vary over great distances. But as long as it's a reasonably regular vector field, and I do need it to be continuous, make things work out nicely, over the very short distances that are permitted inside of this very small little piece of area, it's pretty close to constant. Not exactly, but, not far off. Again, round-off errors are going to go away in a limit. So again, we're stealing ideas from Chapter 6. And I'm going to skip over one point and then just come down here real quick for just to kind of get to complete that thought. If you know the vector field and the area, we have a pre-existing formula for how much flux goes through that little piece of area. It's field dot normal vector times area. So this is just, again, shameless ripoff. And reminder, that's kind of what we did over here when we were talking about line integrals. We said, look, this is not exactly flat, but it's pretty close. And the vector field isn't exactly constant, but it's pretty close. And so, again, we can use the old formula. Same story, same basic idea. Okay, so what's the deal with orientation? Y'all remember when we were talking about line integrals? We were computing work. Work says how much energy do I have to burn? You know, if I'm driving my electric car on this road, how much battery charge am I going to lose by going up this hill? Well, I'm going to lose some battery charge. But wait a second, if I go down the hill, electronic braking and all that clever stuff, it actually charges the battery. So I gain it. So which direction you're going matters a lot, to the tune of a minus sign, right? But, a minus sign, it's a small little bit of algebra, but it makes a big difference in terms of what your actual answer is. So it's very, very, very important. So we had to come up with this idea of an orientation on a curve, right? So we needed the curve not to just be just an inert curve. I need to attach this idea of which direction am I going along the curve. That's got to be part of the calculation. Okay. Same with surfaces, as it turns out. If I've got a little piece of surface right there, and I want to know how much fluid is passing through that little piece of surface, well, which way? Right? I mean, if I've got a little, let's say a little piece of surface like this, there is something qualitatively different about fluid flowing that direction through the surface versus flowing that direction through the surface. Again, to the tune of a minus sign. Right? So, but the point is these things are different, and if they're different, we need to decide in advance, which one are we going to call positive and which one are we going to call negative? And the answer is that we do this by taking our surface and attaching what we call an orientation And an orientation is represented by what we call orientation unit normals. These vectors are what make what had been just a surface now an oriented surface. All right, and it's just a way of keeping track of which direction we're going to call the positive direction through the surface. Just like capital T, when you're talking about curves, is our way of algebraically getting it on paper what we mean by what is the positive direction along the curve. Okay. Now, just a quick little bit of satisfaction. I claim that actually you can see that in action right here. That when I compute this little piece of flux, I've got my vector field like that, and if my unit normal, my orientation unit normal is like this, well, that you can see here, that dot product is going to be positive. The way I have the field drawn here. Right? Those vectors, angle between, acute angle, cosine, all that business, right? Positive dot product, appropriate to the fact that, look, check it out, legit, the fluid is flowing in the direction that we're calling the positive direction through that surface. So it comes up with positive as it is supposed to. And now, just for clarity, what if the vector field was going the other way? Let's see here. Okay, let me do this. I'm gonna just do that real quick. Pull a little fast one. What if the fluid was going that way? Well, if the fluid is going that way, two things I can see. For one thing, that dot product's going to be negative. But for another thing, good. It's supposed to be negative. Check it out. The fluid is literally going in the direction through the surface that is opposite of what we've decided to call the positive direction through the surface. So, perfect, right? So this deciding on a orientation unit normal does imprint upon our calculations a plus and a minus appropriate to that telling us what's the positive direction through the surface. Okay. All right. So it's all over but the shouting. We want to know the total flux. We're going to add up all these little pieces of flux on each little piece as we've just discussed. We get that. And that gives us an expression here that, you might be tempted to call this a scalar surface integral. Looks like a scalar surface integral. It's an integral over a surface. What appears to be the differential appears to be a scalar. What appears to be the integrand, it's a dot product, so that is also a scalar. It looks like a scalar surface integral. I think it's very, very healthy to recognize that there is nevertheless something really different about this integral. Right? This integral, unlike every scalar surface integral we saw before, this integral depends on what choice of orientation you make. You have to choose an orientation to even start on this calculation. And that orientation amounts to a plus or a minus, and it's recognizing that there are different directions through the surface. What's that have to do with mass? Right? Did we consider what direction somehow we were adding up the mass? No, silly. That nonsense. There's no notion of orientation here. Right? Scalar surface integrals don't involve orientations at all. So I feel that this is an illusion. That's a deceptive, that's going to take you down what I consider to be a bad intuitive road. If you try to think of this as being a scalar surface integral, it's importantly different. And when things are importantly different, I think they should look importantly different. Right? If something matters, you want to be aware of it. And the way we're aware of things is by labeling, by making it unambiguous. We want, at a casual glance out of my peripheral vision, I want it to be unambiguously clear what kind of a critter this is. And so I like to write this a little bit differently, like so. And all we do, really no big deal, is we recognize that this stuff together, not just the ds scalar, but the normal vector times the ds scalar. That's what's telling me about little pieces of surface, right? The normal vector doesn't have anything to do with the vector field. The vector field exists independent of the normal vector. The normal vector is telling us about the surface. It should be attached to other stuff that we are talking about the surface, right? And so I like to rewrite all of that as the ds vector, like so. I think it's extremely natural. And by the way, again, there's kind of a shameless ripoff going on here. Flashing back to line integrals. Let's see, let me squeeze it in here. When we were talking about line integrals, there's an alternative way that we can write a line integral over a curve. We would write that as f dot t ds, but it's better, I think, personal preference, to write this as f dot dx. And so notice we're doing the same move in the same way that we took TDS and recognized, look, that's really much more naturally understood as the dx vector. Likewise, we're taking in d capital S, and I'm claiming that is much more naturally represented as the d capital S vector. So not our first time. Is that cool? Okay. Alrighty. So with that in mind, let's see here. Oh, and now I've made a mess. Let's see. I gotta do that, and then I can do that. Now that we have it written in a reasonable way, still a surface integral, of course, but now vector surface integral, because the integrand and the differential written in what I consider to be the most natural way. Vectors, not scalars. Everybody on board? By the way, let me further recognize, when we did this same calculation back when we were looking at work, we didn't enter into this work computation with like a goal in mind of I'm going to create a new kind of an integral. It just kind of happened. It just fell into our laps. Well, I guess that's what it is. Oh my gosh, look at that. It's a new kind of integral. And that's the same thing that's happened here. We didn't enter into this flux computation with an agenda to make up a new kind of integral. We just want to compute flux, and we followed our nose, did what seemed reasonable, and oh my gosh, look at that again, new kind of integral. So again, totally analogous in a natural way. All right. Okay. And good news, we already know how to compute this stuff. We have everything that we need. In fact, these are actually really easy calculations in many cases. Because don't forget, we've already talked about parametrizing surfaces. We've already talked about stretching factors that turn input areas into output areas. We've got all the groundwork for that. It's all laid. Yeah, magnitude of capital N. Capital N is the cross product of the partials. It's all there. All we have to do is actually just kind of literally to plug that into our formulas. And now this is just a recopy from above, straight up recopy, nothing new there. This is the formulas we had at the bottom of the previous page. And if I just do this, if I just take this formula, ds scalar is magnitude of capital N times ds dt, like so. It's, again, we already had that. I'm just plugging it in. Check this out. What can I say about this product? Well, I've got a unit vector times a scalar. Unit vectors define directions. They have magnitude 1, so when I multiply by a scalar, the scalar is the magnitude. This is a vector that points in the direction of little n and has magnitude the same as capital N. Let me say that a little bit differently. This is a vector that points in the same direction as capital N and has the same magnitude as capital N. This agrees with capital N, so it seems, in both direction and magnitude. It looks like a duck and quacks like a duck. So it's capital N. What do you think? You buy it? By the way, let me confess before anyone catches me. I did just commit a math crime. I did just make an oopsie on purpose. Did it on purpose. Right? I like to commit this math crime for two reasons. One is sort of a dramatic reveal that's going to come up in a minute. But the other is we've got enough going on, and the subtlety of what's wrong with what I just said is going to just make things more confusing. I think we're better off dealing with what we got, right? And then we'll worry about subtleties in a minute. So I'm just going to sweep this under the rug, but again, full confession, math crime, details of the crime to follow. Seeming punchline, if you want to compute a flux, we've got a formula. And notice this formula is all in terms of the pullback. Everything's in terms of the parameterization. The parameters, S and T. Capital N comes out of the parameterization. F is a function of X, Y, Z, which are functions of S and T. All of that is in terms of S and T, and you can totally plug and chug. That's the plain old double integral. Totally doable. Let's do one. All right. Let's see here. How we? Okay. Yeah, we'll make it here. Vector field. We've got surface described here. Ooh, cool. Check it out. It's a graph. I love it when that happens. It's a graph. That means I can use the graph parameterization. Right? Sweet. And let's see here. Yeah, so we're computing the flux, and we're going to compute the flux with the formula we just wrote down. There's the formula we just wrote down. Yeah, apparently I am going to need my capital N. So, okay, we've got to parameterize, compute the partials, compute the cross product to get my capital N, which you see I just totally just computed and plugged in. Let's see here. What's with the F business? F is this. Why does it look so different? Well, what is Z? Anyway, comes from the parameterization. Don't forget, right? The parameterization literally tells you what X, Y, and Z are. So apparently Z is S squared plus T squared. And then, by the way, what's X? Well, it says right here in my parameterization, X is S. Is that cool? Everybody see what's going on there? It's just plugging in. You got to be careful because it's easy to mess that up. And then the last little detail is where do these bounds come from? And the bounds, 0 to 1, 0 to 1, come from the fact that I'm looking for the range of values of S and T. S and T are literally X and Y. So I need to know what's the range of values of X and Y, and it says right here, above the unit square is where X and Y go from 0 to 1 and 0 to 1. And so there's that integral. And this is a plug and chug double integral at this point, totally compute. It's just a polynomial, totally doable, and that answers this question. Okay, natural stopping point, and we will pick up here on Tuesday. See y'all later. Have a good one.